Hello, everyone. Welcome to Luohan Webinar. Today, we are very happy to have the Professor Justin Johnson. Justin Johnson is a professor of economics at Cornell University's Samuel Curtis Johnson Graduate School of Management. He's an active and globally renowned researcher in economics and strategy, and a past editor at both Journal of Industrial Economics and International Journal of Industrial Organization, which are top journals in his field. And Professor Johnson uses a tool from economics and game theory to better understand how firms can compete and succeed in challenging environments and what strategies they can adopt to either achieve or maintain dominance in markets. Today, he is going to talk about the platform design when sellers use pricing algorithms. So, Professor Johnson, the floor is yours.
Thank you. And as you can see, this is joint work with some really excellent colleagues of mine. And I'll just jump right in. These days, I'm very interested in digital competition issues. And so this paper is related to that. As we all understand, products are increasingly sold through online marketplaces. And more these sellers, these third-party sellers are using algorithms to set and change prices. Now, there could be many benefits to algorithmic pricing, without question, but there's also some growing concern that perhaps algorithms might be used for less positive reasons. And so there are a number of policy reports and investigations, in various antitrust regions. There's even been some cases involving algorithms used for anti-competitive purposes. Topkins in the United States and Eturus in the EU both allegedly involve basically hub and spoke style conspiracies where algorithms sort of enable or facilitate collusion amongst members. And actually in the United States, there have been some recent reports of another situation in which algorithms are facilitating collusion. I'm not going to talk about that. We're not focusing on the kind of a hub and spoke style situation. We're more interested in situations where the algorithms themselves, even without being explicitly trained to collude, might nonetheless exhibit emergent behavior that looks somewhat like collusion. So the concern that we're going to focus on, which is really first highlighted by some legal scholars and also in economics by Klein and Calvano and his co-authors, again, suggesting that perhaps, algorithms, artificial intelligence algorithms specifically might learn to collude and thereby harm consumers. And so that's the sort of situation that we're going to be considering. And I'll tell you more about that as we go along. But our question or our main motivation is to ask, well, hey, if we are in a situation of an online marketplace with third-party sellers, how can the design of that marketplace influence the competitiveness of market outcomes? Okay, and we can think about platforms as being similar to regulators who can design the rules of the game governing how buyers and sellers interact on the marketplace. Okay, and so we're going to specifically consider situations where the platform has some ability to steer demand or otherwise nudge consumers towards certain products. And just to give you a simple example that's sort of related to what we're doing, it's not exactly the same, but similar. I don't know if Alibaba, has a similar thing, whatever, but this is Amazon. Amazon has something called the buy box. And if you go to the Amazon marketplace and you search for a particular item, in this case, a 3-pack of chapstick, which is a lip balm that you put on your lips in the winter, you click on one of the links that the search generates, you'll get a page like this, okay? And it obviously tells you a little bit about the product, but then over here to the right, you can add it to the cart. And the key thing is if you add it to the cart, you're actually choosing to buy from a particular merchant. Now, it turns out that there are a number of merchants that sell this product. There's, I guess, at least a total of 4 that sell it new. but one of them is being highlighted up in the top right, and that's called the buy box. Now, if you don't want to buy from that merchant, you don't have to. You can go down here a little bit, and if you poke around on the website, you can find the other sellers, okay? But you're clearly sort of being suggested to you that really perhaps you ought to buy from this particular merchant, okay? Now, whoever wins the buy box is thought to get a very large amount of the demand for that product at any point in time, maybe about 80% of the demand. So most consumers just click on the buy box and say, okay, I'll take that. Now, how is the winner of the buy box determined? Well, the truth is we don't know exactly. We know that price plays a very important role, but price is not the only thing that matters. Okay, so this is just a simple example of a platform steering consumers in a certain way, and that's in some sense part of the motivation for our paper. Now, when we're going to look at a couple more sophisticated steering mechanisms. I should say right now, this example here and all the ones on Amazon are for a very specific product, and so anything they're showing you here is undifferentiated. So everything is exactly the same product, namely a 3-pack of chapstick. What we're going to be doing is looking at products that are actually differentiated and see if we can generate similar steering technologies that ultimately benefit consumers. Okay, and we'll talk more about that as we go along. So that's what we want to look at. We want to consider simple, fairly simple steering technologies that a platform could use. We're going to examine their theoretical effect using a game theoretic model. And then we're also going to examine their effect when sellers are using AI algorithms, specifically a simple type of AI called Q-learning, to set their prices. And so we're going to see, hey, how do these algorithms respond when the platform introduces these steering technologies? And what we're going to show is that, at least in some cases, thoughtful platform design can not only benefit consumers, but additionally increase the profits of the platform, okay? And these policies are interesting to us in that they do, by design, limit consumer choice and sometimes treat sellers in a non-neutral fashion. So despite these things that we sometimes might think of as bad, again, limiting consumer choice, treating sellers non-neutrally, in our model actually have positive effects. I'm not really going to talk about these papers, but there are a number of papers. I should say it all starts with some of these legal scholars that I mentioned at the top, like Mehra and Azraqi and Stuck. And that's kind of generated a growing literature in economics and computer science about algorithms, collusion, and so on and so forth. I will just highlight one more time this paper by Calvano and his co-authors, now published in the AER. And what that paper does, it's similar in spirit to what we're doing. They take these algorithms, these Q-learning algorithms, which is a simple type of AI, and they don't train them to collude, but they just kind of let the algorithms run out and do whatever they do, and they learn and they figure out whatever it is they want to do because they're AI algorithms. And what Calvano and his co-authors find is that they actually learn to charge very high prices that looks a lot like collusion. Okay, so again, we're not specifically interested in a situation where we're designing the algorithms as such to collude, but more in a circumstance where the algorithms sort of end up doing something that looks like collusion. And then we ask, hey, what can we as the platform perhaps do about it? Okay, so my game plan here, and I have a lot of slides and I probably won't get through everything, but I'll try my best. First of all, to give you the basics of the theoretical model, and then I'll talk about the specific types of algorithms that we're going to be using, okay? And then I'll give you results on kind of what happens when we actually use our demand steering with these real algorithms. And then I have a few extensions, okay? So that's where we're going. Let me just start with the theoretical model. And again, our goal is to think about an online marketplace, analyze certain demand steering interventions from a theoretical perspective, and then also see how those same demand steerings work with AI algorithms. Okay, so the theoretical model, I'm just going to give you a quick summary of it. There's some number of firms. They're sort of symmetrically differentiated, and they sell on some monopoly retail platform, such as Amazon. They all have the same positive constant marginal cost. And this is going to be inclusive of any platform fees. I'm not going to talk a lot about the platform fees. If you're very interested, you can look at the paper. We talk a lot more about that in the paper. Anyway, these sellers interact repeatedly over time. And in each period, each firm can observe everything that's happened in the past. And they all set a price in every period, and they share a common discount factor delta. Okay, so in some sense, it's a very simple repeated game. The consumers, how do they work? Well, in each period, a new group of consumers arrives in the market, and they want to buy at most one product. And there are these end sellers. Again, the products are differentiated. Let me emphasize that again. And they're differentiated according to a standard discrete choice framework, in particular a logit framework, with what I'll call differentiation parameter mu. Okay, so the higher that mu is, then this kind of standard logit model, the higher firm markups would tend to be. Okay, so it's on the consumer side, it's a symmetric differentiated logit model. If a consumer doesn't buy something today, they just disappear. Okay, and then tomorrow a new group of consumers arrives. So there's no storing of goods or waiting or anything like that. What does the platform want to do? Well, again, as I said, I'm not going to talk a lot about the platform's objectives. That's in the paper. If you're interested, we have a lot of stuff on that. But just briefly, what you should imagine is that the platform cares about a weighted sum of consumer surplus and the total fees or commissions that the platform generates. And so what we're going to focus on for this talk, or what I'm going to focus on, are per unit fees. Okay, so every time a merchant sells something on the platform gets a given a fee for each unit. Okay, now we could also think about revenue sharing, and if I have time, I'll talk a little bit about that at the end. Okay. So, but anyway, the platform cares about consumer surplus to some extent. How much is just a parameter, and they also care about the own fees. You could think about the consumer surplus as being a proxy for caring about competition, right? If I try to take too much from consumers today, I'll lose demand to whatever Walmart tomorrow. Okay, and the platform, their main power here is that they can choose certain display rules or demand steering. Okay, and just to be clear, consumers can only buy a product if the platform chooses to display it. Okay, and we're going to consider three ways this subset of products could be generated. The first is just, the platform just shows all the firms, all the merchants. The second is what we call price-directed prominence, and then third is called dynamic price-directed prominence. Okay, and I'm going to start with the first one, which is called price-directed prominence, or PDP. Okay, and again, the way this works is very simple. In each period T, the merchants all set their prices, and then the platform says, I'm only going to show a subset of you. I'm only going to show K of you, where K is less than N. And the way I choose which K firms to show is by simply choosing the firms with the lowest prices. Okay, so I'm going to take the K lowest price firms. If there's any ties, I break them randomly, and I'm going to show these K firms to the consumers. All right. And if you're not, again, to emphasize, if you're not one of those K firms, then your product is not shown to consumers and you get zero profits that period. All right. So you can work out pretty easily what happens from a theoretical standpoint. Well, let's first of all suppose that sellers are competitive. So they kind of compete in each period pretty strongly. Then, without this demand intervention, without this steering intervention, all the firms are shown, and because they are differentiated, they all charge some markup over cost. So they all charge some, let's just call it P, some price P, which is strictly greater than cost. Once the platform implements price-directed prominence with only K firms being shown, then each firm faces a tough situation. It says, look, if I'm not one of the K lowest price firms, I'm not going to get shown to consumers at all. And so I won't get any sales today. And so intuitively, what's going to happen is the firms are going to compete to be one of the K firms that are shown. And that's going to lead them in equilibrium to all charge marginal cost. So that sounds like it's great for consumers, right? Now the prices are marginal cost, so they're lower than before. However, the products are differentiated, so consumers also have less variety to choose from. So there's actually a trade-off in terms of consumer surplus. And what you can show is that, consumers benefit as long as you show enough of the firms. You can't show all N, right? If you show all N, then the firms are going to charge a markup. They're not going to charge marginal cost. But let's suppose you show like N minus 1. So suppose that K is equal to N minus 1. Then that's actually really great for consumers because they lose a little bit of variety, but they get all the products at marginal cost. And so there's some cutoff rule basically says as long as you don't obscure too many of the options, then limiting choice in this fashion benefits consumers. Okay, and that sounds good.
Sorry.
Yeah, go ahead.
Hi, Professor. Can I ask one question? If you
Sure.
go one slide. So here you assume that the marginal cost is the same for all the firms, right?
That's right. That's
then
correct.
we think in general that marginal cost will be like positively correlated with the quality. Then in that sense, you're gonna lose all the high quality.
Yeah, I think that's a great question, and I agree 100%. We talk about this a little bit at the end of the paper. Yeah, so I think in practice, if you really wanted to implement tools like this, you'd have to be very thoughtful about quality differences between the firms. And we haven't worked it out, of course, fully, but you can imagine that what you would like to do is maybe sort of estimate, for example, the quality differences between the firms, and then use a modified rule that's not based solely on price, but on some sort of quality normalized price. But yeah, you're exactly correct. If you're not careful, this is going to have bad outcomes. I completely agree with that. Absolutely.
Okay.
So you have to be a little bit more careful in practice. Yeah. But taking that as a given for the talk, again, supposing that the platform maximizes a weighted sum of consumer surplus and fees, remember that the total fees of the platform, because they're per unit fees, they're going to increase with output in the same way that consumer surplus increases with output. And so, as long as the sellers act competitively and you don't hide enough sellers, then not only do consumers benefit, but the platform also benefits here. Okay, so the payoffs of the platform go up, consumers are better off. Moreover, as we talk about in detail in the paper, as the number of merchants N gets fairly large, not only does PDP benefit consumers and the platform, but it's almost as if the platform can extract all of the surplus from sellers and really make, and also basically what happens is the seller's surplus goes down and the consumer surplus and the platform's profit basically approach 100% of the theoretical maximum. Again, that's in the paper. I don't have time to go into the details of that, but all that's to say that even though PDP is a simple policy, and you can imagine more sophisticated policies that perhaps would do better, what we can show is that actually PDP does quite well in terms of seizing a large portion of the percentage gains that it would be possible, even if you had arbitrarily complicated schemes. Okay, so that sounds good, subject to, some, caveats like, different costs and qualities. But hold on, we've been assuming that sellers compete in each period. What if that's not true? Okay, so the next question we ask is what if just the opposite is true? What if the merchants form a cartel? And we're going to focus on the full collusion benchmark, where the firms value the future high enough that they can perfectly collude today. All right. In that situation, if you implement PDP, price does still fall, okay, but it doesn't fall enough to benefit consumers, okay? And so in that situation, basically, if you have a cartelized market, actually PDP is bad for consumers, okay, and also bad for the platform. And so now it's a little less clear. Well, geez, is this a good policy? Is it not a good policy? It's a little less clear. And so we want to be open. We want to be open to the possibility that sellers collude, because again, this literature sort of starts thinking about the prospect of algorithms learning to collude. So we don't just want to assume that the algorithms or the merchants behave competitively. And so we're going to introduce our second policy, which I guess you can't see because of the zoom bar, but it's called dynamic price-directed prominence. Okay, so it's like the previous one, and here it is in detail. I'm going to let you read that. I'm not going to. Yeah, go ahead. Yes.
Yeah, because you didn't show the proof, so I'm wondering, could you explain a little bit more about intuition? Why the algorithm will, limited the choices of consumers will increase the consumer class, and what do you mean exactly by saying the sellers are collude? How they collude? Yeah, that may help me to understand.
Sure.
What would be your propositions? Yeah. Thanks.
Yeah, absolutely. So let me back up to the case where the sellers behave competitively. Okay, so again, without PDP, even though they're competitive, their products are differentiated, so they're charging some positive markup over cost. Let's suppose there are 10 firms. Okay, and let's suppose now that PDP hides only gets rid of the highest price firm. Then in each period, consumers are still going to see 9 of the 10 firms. So they've lost a little bit of variety, but not a lot. Okay. However, no firm is charging a positive markup now because they're all competing to be one of the 9 firms that are shown. They're lowering their price and lowering their price, and eventually they're all charging marginal cost. And so what happens is the consumers have lost a small amount of variety. Okay, but the prices have fallen all the way to marginal cost. And so it's just, you can compute, that's a trade-off, and in the logit model, you can compute it. And again, as long as you're not hiding too many firms, the consumer surplus increases. Okay. Now, in terms of the cartelization, yeah, for now, we're really not even thinking, I keep saying algorithms, but for now, we're not even thinking about algorithms. These are just kind of standard economic agents, merchants. And so the way that they're colluding is kind of in the similar economic style, which means they all agree in the absence of a seller of a platform intervention, they're all agreeing to charge high prices, very high prices, higher than they would in a competitive setting. And what happens if any of them thinks about lowering their price today, then basically they start a price war that lasts, into the future, and that price war is no good for any of the merchants, and so that incentivizes them all to keep prices high, and that's what the collusion looks like. Okay, now PDP, so you can think about the collusion framework. The intuitive way to think about it is now that there's a single firm that controls all N of the products. Okay. And now what happens, and so they're going to obviously raise their prices very high. And now what they're going to do if the platform implements PDP and only shows 9 of the 10 products, that multi-product monopolist is still going to find it optimal to lower prices a little bit because it's almost like it has less variety now. And when you have less variety, you tend to want to lower your prices. But they're not gonna lower them all the way to marginal cost because they're still able to collude. And so on net, consumers actually don't benefit. That variety loss is so big or big enough that it doesn't overwhelm the small decline in prices. Okay, I don't know if that, hopefully that helped. But anyway, we don't like the idea that collusion might exist, and so we want to actually have another policy that's designed to attack collusion directly. And so the second policy is called dynamic price directed prominence, and it's a little bit more sophisticated. Basically, what happens is in the first period, all the firms set their prices and the platform goes to the lowest price firm and it says, I'm going to give you an advantage. I like what you did, you charged a low price, I'm going to give you an advantage just to one of the firms. Okay, and then that advantaged firm now has a special, advantage in future periods. As long as it doesn't raise its price, and as long as no firm undercuts it by a large amount, this ADV amount, then that firm is still going to get shown to consumers. All right. And if either of these conditions ever fail, then basically the platform rewards the advantage to another firm. Don't worry so much about the details about that. Let me explain the intuition behind this new policy. Okay, let me first of all tell you what the new policy does. If you implement this new policy, dynamic price directed prominence, and you have a sufficiently large, ADV value, then it turns out that collusion is impossible. Okay, no matter how patient the firms are, then in any pure strategy, subgame perfect Nash equilibrium, the transaction price is marginal cost in all periods. So basically, you can now, even though you face a cartel as the platform, you can force the cartel to price at marginal cost. You can basically break collusion, and that will typically benefit consumers. Okay, why does this work? The intuition is the most important thing. Remember how a cartel works normally. I said a few minutes ago that the reason a cartel can keep prices high is each firm says, if I cheat on the cartel and I lower my price, I'm going to start a price war, and that price war is going to hurt me. So it's not worth it for me to cheat on the cartel today. All right. And what dynamic PDP does is it makes it hard to punish firms that deviate from the cartel. If I deviate from the cartel, well, you can't necessarily punish me unless you charge, a lot lower than what I'm doing. And that often will not actually happen. Okay. So what we have then, let me just summarize, because I know maybe it's a little confusing quickly. We have two policies. One is called PDP, which just shows the lowest price firms. The other is dynamic PDP, which is a little bit more complicated, but basically it's built specifically to attack the foundations of collusion. And now what I want to do with the rest of the talk is discuss a little bit about how we're going to test all of this using algorithms, and then tell you what we actually learn from using these algorithms. Okay, so those were theory models, but for everything I'm going to do going forward, I'm actually going to talk about actual algorithms and how they respond to these demand steering technologies. Okay, so I'm going to talk about a particular type of AI called Q-learning. You may be familiar with the game of Go, and you may know that Go is a lot more complicated than chess, which is popular in the West because the game of Go has a vastly larger state space than chess does. And so for many years, even though computers were very good at playing chess, it was believed that computers could not learn to be competitive at Go. And about, I guess 6 years ago now, all of that changed, and a company now owned by Google called DeepMind basically had their Go algorithm called AlphaGo play one of the best all-time Go players, this Korean guy called Lee Sedol, and basically the algorithm won 4 of the 5 matches. Okay, and today that algorithm is just a lot better than it was 6 years ago. And so humans really, as far as I know, I'm not a Go expert, but as far as I know, the best human players in the world basically have no chance against this particular algorithm. Okay, now we're obviously not doing anything nearly as sophisticated as that. We're going to use a super simple version, but it's still kind of motivated by some of the same technology that's used by AlphaGo. But of course, it's just infinitely simpler what we're going to do. And we're going to talk about Q-learning, okay, which is a particular type of artificial intelligence, and I'm going to tell you how it works. Okay, so and this is what computer scientists use this in a broad range of algorithms. I should emphasize that Q-learning is particularly powerful in situations where you're just not really sure how the environment works. You don't know how it works. You want to try to do well nonetheless. What can you do? Well, computer scientists have an answer, and it's called reinforcement learning, or specifically Q-learning is what we're looking at here. Okay, so suppose you have a decision problem that evolves over time, and in each period you have a finite number of actions, X, that you can take, and you face a finite state space. And in each period you get some, possibly random payoff that depends somewhat on the state and the action that you took. All right, and there's some state transition probabilities, could be, so some stochastic transition probabilities between states. What do you want to do? You want to maximize your discounted payoffs, but you initially don't know anything. Suppose you don't know the payoffs, you don't know this pi function, you don't know the transition probabilities, you don't know anything except that you can take these actions and that you have these states. And that's all you know. What are you going to do? Well, you want to try to do as well as you can. So you want to try to learn from past experience. Since you don't know anything at the start, all you can do is try to learn from your own experience. And in particular, what Q-learning tries to do is iteratively estimate this particular function, which I call Q star here, called the action value function. It's important to understand at a theoretical level what this is. By definition, Q star of S of X is your expected payoffs if you're in state S today, and you take action X today, and in the future, you follow the optimal policy, whatever that optimal policy might be. You don't know it, but if suppose somehow you could follow that policy in the future, that would give you this function Q star. Now, if somehow you were able to accurately estimate this Q function, I'll just call it the Q function, you would then know the optimal policy. Right? If you could somehow find this Q function, you would know the true optimal policy. All you would do is in any period, you'd say, well, geez, I'm in state S. This Q function is just a matrix because there's a finite state space and a finite set of actions. So I'm just going to look down this matrix to find the row that's corresponding to the state that I'm in today. And then I'm just going to read across that row until I find the highest value, and whatever actions associated with that highest value is the action that I should take. Okay, so if I could somehow recover this Q function, I would actually have a full optimal solution to this decision problem. Okay, well, yeah, but if I knew the function, I wouldn't be doing this in the first place. So how can I learn it? And you learn it in the following way. You start with some arbitrary matrix. Okay, and say I don't know anything, but I'll just start with this arbitrary matrix. And then what you do at time S and in state S is you basically flip a coin, and with some probability epsilon t, you're going to randomly choose an action, and otherwise you're going to choose whatever action is best according to the current Q matrix. All right, and now you're going to update this Q matrix over time, hopefully in a way that converges to the true Q matrix. All right, and so the way you do that is as follows. Suppose you're in state S, you took action X, and you actually observe your payoffs. You say, I got $5 today, all right? And I see that I've transited to this new state S prime, okay? Then I'm gonna update exactly one of the cells of this Q matrix, particularly the one corresponding to S and X. And how am I going to update it? Well, the value on the left is the new value, the updated value. This is notation from computer science. And then on the right, basically all I do is I take a convex combination of two things. First of all, I put some weight on my old value. And then over here, I basically say, well, the value I'm going to place is based on the payoff that I actually observed, because I actually observed, I got $5 today. So I say, oh, I got 5. And then the other thing is, I look at my Q matrix and I say, geez, I'm in state S prime now. According to my Q matrix, the best action to take is say X twiddle, and that gives me some other value. And I just take this convex combination. Now, if you remember your dynamic programming from graduate school, if you had that, this might look a lot like a value equation, and it is. And so the good news is that if you just repeat this process iteratively, then under mild assumptions, you're actually guaranteed to converge to the true optimal solution in a single agent setting. And in multi-agent settings, it's more complicated, but we'll show that you at least always get convergence in the settings that we look at, okay? So this is exactly the type of algorithm that we're going to use. Specifically, I'm going to tell you now exactly what we're going to do. We're going to have 2 algorithms. For almost all of it's actually for everything I'm going to talk about today, there's 2 algorithms, there's 2 merchants, okay, a total of 2. Each of them is running a Q-learning algorithm, okay? And they're trying to figure out, what to do. And so they're just going to do exactly what I just described. They're going to, take an action. Sometimes they're going to randomize. Sometimes they're going to take the action that they currently think is best, given whatever the state is. And they're going to do that over and over and over until they exhibit convergence, okay? And the only thing I'm going to do that's a little bit different from the theory model, and you can actually forget more or less everything I told you earlier and just focus on this one parameter, gamma. This is the main parameter that I'm going to change for the rest of the talk. And gamma is going to be the intensity with which the platform implements these demand steering policies. So if gamma is equal to 0, there's no policies whatsoever. There's no demand steering whatsoever. If gamma is equal to 1, then 100% of the consumers are subject to demand steering. If gamma is somewhere in the middle, like gamma equals 1/2, then basically what happens in every period, half the consumers see all of the products or both of the products, and half of the consumers are going to be subject to demand steering. So for example, half the consumers will only see the low priced product, okay? We're going to discretize the state space and to have 15 pricing elements. This is a little bit about the marginal cost of firms and lower than the full monopoly price. So the state space in every period is the set of yesterday's prices. Okay, so in each period, each of the two algorithms say, well, what was the price? What were the prices yesterday? And then they're going to use that as a basis for today's prices. Since there's two firms, that means there's 225 elements in the state space. We're just going to run these algorithms until the strategies converge. And then we're going to compute, market prices, consumer surplus, stuff like that. And then we're going to reinitialize the algorithms and start the entire process over. And we're going to do that 1,000 times. Okay, each time resetting the algorithms and forcing them to learn and converge once more. And then we're going to ultimately average over all of this. Okay, and those are going to be what we'll call our experimental outcomes. All right, and we're interested again in seeing how our two demand steering policies actually affect the market. Okay, so let's just jump right in. Okay, just a little bit more. I should say one more thing, which is I'm going to use a discount factor of 0.95. Okay, because the algorithms have a discount factor. I'm going to use a discount factor of 0.95, cost equal to 1, and mu is equal to 0.25. Mu, remember, is the differentiation parameter. Okay, and let's just kind of see what happens without any of the algorithms. In the absence of the algorithms, the AI, the charge, as you can see over here to the right, the algorithms converge to a price about 1.68, which is kind of roughly halfway between the theoretical Bertrand-Nash price and the fully collusive price. Okay, so the algorithms, they charge higher prices than theory predicts. They don't get all the way to the collusive price. What happens as we implement PDP? Okay, so remember, the one parameter you want to keep in your mind now is gamma, which is going to be on the x-axis. When gamma is equal to 0, there's no demand steering. When gamma is equal to 1, then 100% of the consumers, in this case, only see the low price product, okay? And when gamma is equal to 1/2, half the consumers see both products and half only see the low price product, okay? So you can see what happens as you increase gamma so that you implement the steering policy on more and more consumers. Prices, first of all, they go up a little bit, but then they go down, okay? And that seems good, prices are down, but what happens to consumer surplus? If you look in the right panel, you see that actually consumer surplus goes down when you implement this policy. In other words, you'd be better off not implementing the policy, which would be gamma equals to 0, than you would choosing any positive value of gamma, okay? And that's actually consistent with our theory, which is that, in cartelized markets, if you implement PDP, prices go down, but they don't go down by enough to benefit consumers. And in this case, you can see the prices, they don't go anywhere near marginal cost, in fact, which is equal to 1. And, consumer surplus goes down by about 6.5%. So that's unfortunate. That means this policy, it means the algorithms, at least with a high value of delta, they seem to be operating kind of like a collusive market in the sense that this policy is not benefiting consumers. Now what I want to do is I want to look at what happens when you vary the discount factor delta that the algorithms use, okay? Because again, the algorithms use this discount factor when they compute their Q matrices, okay? So in this left-hand panel, on the x-axis, we have gamma, and on the right, the bottom axis, the x-axis, we have gamma, and on the vertical axis, we have the discount factor delta. And red colors are higher values of consumer surplus, and blue colors are lower values of consumer surplus. So this is the level of CS. And the way I'd like you to read this is to just choose your favorite level of gamma, okay, on the x-axis, and then kind of go up and down the graph. And you can see what happens is that means that as you raise delta for any given value of gamma, consumer surplus goes down. And that's consistent, of course, with the theory of cartelized markets, the economic theory of cartelized markets, which generally says it's easier to sustain a cartel when you have a higher value of delta. Okay, so this says these algorithms kind of behave in a sensible fashion. This graph, it's actually the same data, it's just colored differently. The way I'd like you to read this one is choose your favorite value of delta on the vertical axis, and then look at what happens when you increase gamma. And what you can see is that generally, as you go from left to right, the colors turn from green, generally turn to yellow or red. And what that means is that there's some value of gamma that actually benefits consumers. And this is true unless delta is greater than 0.9. So in other words, if delta were lower than 0.95, well, lower than 0.9, there would always be some gamma that the platform could choose such that prices fell enough that overwhelmed the variety loss and made consumers better off. Okay. So that seems well, it's good. It's good, I guess, if the algorithms don't have a high value of delta. But I just showed you a few slides ago that when delta is 0.95, consumers are worse off. So this is sort of reassuring in some sense, but on the other hand, it's still not great news. I want to quickly show you one more thing with PDP, which is that if we consider a lower value of product differentiation than before, then actually we can find a situation where not only do prices go down, but consumer surplus goes up, again, as we increase gamma. And this makes sense because remember, the trade-off is lower prices versus less variety. So if the products are less differentiated, then in a sense, you lose less variety when you hide firms. And so in this case, consumers are actually better off. All right. So actually, I should show this. So this is what we've learned so far, which is basically that PDP sometimes works, but sometimes it doesn't. Sometimes it actually hurts consumers, and it tends to hurt consumers when delta is pretty high, and when differentiation is pretty high. So we don't like that. Again, we have the second policy. Remember, we have this second policy called dynamic price directed prominence, which is a little more subtle than just showing the low price product in every period. And recall that we built this second policy specifically to attack collusion. And so we're going to say, let's see what happens when we deploy this more sophisticated policy. And we're going to go back to the original parameters where the simple policy hurt consumers. And so we're going to show the same things here. Now, the blue line is the first graph I showed you earlier, where prices go down, but not enough to benefit consumers. The red line is what happens under the new policy. And you can see what happens to prices. Initially, prices kind of look sort of similar to the PDP prices. But then as gamma gets bigger and the platform, exposes more and more consumers to this demand steering policy, basically the algorithms quickly learn that they need to set very low prices. And so prices fall quite a lot. And it turns out the consumer surplus goes up quite a lot as well. In this example, price falls by 19%. Consumer surplus is 27% higher. And I should say that total output also goes up. And all this ensures that the platform, as well as consumers, gain from this policy. So this is good news. We're happy to see this. It says, you can actually get the algorithms to behave pretty competitively, but you have to be a little more sophisticated with the policies that you use, at least if you think that the algorithms, have some tendency to, quote unquote, collude. We actually have a third policy, which is the same one as dynamic PDP, but we just let the algorithms behave in a slightly smarter way. And I haven't given you all the information here, so I know it's a little hard to know exactly what we're doing differently. But loosely speaking, what we do is we allow the algorithms to track the identity of the firm that has that special advantage. If you recall, dynamic PDP gives one of the firms sort of a pricing advantage in every period. And whichever firm has that advantage is in a good situation. If we let the algorithms also track which of the two firms has this advantage, then they behave even much more strongly to this demand intervention. And you can see what happens. Prices fall a lot more, not all the way to marginal cost, which is one, but a lot. And consumer surplus, as you can see in the right panel, goes up even higher than before. Okay, so we think this is good news as well, because it says, hey, if anything, if you make the algorithms a little more sophisticated, then they're forced to respond to what theory predicts and behave in a competitive fashion. All right, so there's no questions so far. Then basically what I'll do is I have a few extensions. I'll talk briefly about probably one or two of them. Okay. But so far, let me say, and I know it's a lot to process in an hour because I had a theoretical model, and maybe some of you haven't seen Q-learning before, and that's a lot to process. But roughly speaking, I guess what I should say so far, let me back up, is if the algorithms don't respond exactly the way that theory predicts, that's true. But nonetheless, our policies show some promise in benefiting both consumers and the platform. In particular, the simple policy of PDP, which just shows the low price firm, that benefits consumers, as long as the products aren't too differentiated. Okay. If the products are more differentiated, then you need to use this more sophisticated dynamic PDP policy. And there we get actually very strong results that show that the algorithms seem to, behave actually kind of close to what theory predicts. They lower their prices dramatically, especially when you make the algorithms a little bit smarter. And so far we think that this shows a lot of promise that algorithms can use some of the ideas from economics to kind of steer how demand or how algorithms work on the marketplace. Okay. So
hi, Professor.
Yes.
So I was wondering one question. I'm not sure how widespread the adoption of this pricing algorithms is in the US, but in China, I think it's quite rare that sellers are actually using this algorithm to price their products. But actually, if we think about this, maybe because like if there is a lot of heterogeneity across different sellers, right? Suppose maybe the large sellers, they are more kind of sophisticated. They have this access to these algorithms. What will happen if only a subgroup of buyers or sellers have access to this algorithms? How will
I think it's a great question. I mean, the answer is we don't know. I mean, that's an empirical question. I think it's a very, very interesting one. It is true that the larger sellers are the ones that tend to be using the algorithms because, you can imagine if you've got 100 different products or 10,000 different products that you're selling, it's just hard to keep track of it all. It's true. In the US anyway, again, I can't speak to China, but in the US, there's lots of companies that sell these algorithmic pricing. They're called repricing services. We don't know exactly how those algorithms behave. I think your question is really interesting. I don't know the answer. Again, it's an empirical question. I think it's an interesting one. There are some studies that try to look at the interaction between algorithms and humans. But I don't know that those studies give us any really strong conclusions. Yeah, it's a good question. I will say though, you know, that, well, I guess I'll leave it at that. I want to talk now about pricing patterns. I've talked about price levels and consumer surplus. Now I want to dig into more detail about the actual patterns of prices. And I need to start by letting you know something that I didn't mention earlier, which is if you run a particular set of algorithms, just fixing all of the parameters, they don't always converge to exactly the same thing. Okay, that's why we run the algorithms 1,000 different times for each set of parameters. Okay, so but they converge to different things. So there's some randomness in how they learn. Okay, in a multi-agent environment. All right. And so, for example, sometimes they converge to an outcome where each of the algorithms is just setting a constant price over time. And sometimes they converge to some sort of repeating price cycles. And so we want to look a little bit at how these demand interventions affect the resulting price patterns. And the main question that we're interested in here is whether the algorithms can learn to rotate demand over time. Now, if you're familiar with the theory of collusion, you'll know that a long-standing, you know, theory, which seems to mesh well with empirical observation, is that in a lot of real-world cartels, firms, they rotate demand over time. So they take turns. You're going to set the low price today. I'll set a high price, and tomorrow we'll switch. And they kind of, that's just how they implement their cartel. And in the real world, that often happens. Not always, but often. And, you know, and so we want to kind of look and see what's happening with these algorithms. Are they doing something similar? Remember that these demand steering policies by design, especially if gamma is equal to a high number like 1, by design, the outcome within any given period is highly asymmetric. So suppose that gamma is equal to 1, and we're just using PDP with 2 firms. Then in any period, any given period, only 1 firm is shown to consumers. So the other firm gets, you know, 0% of the market. So, you know, within a given period, these demand steering policies, you know, by design, generate highly asymmetric outcomes in terms of, say, the profitability of the 2 firms. But what happens over time? Okay, so there's a lot to process on this table, so you don't need to look at everything. Just want to look at a few things. First of all, I've got the base policies where you do nothing as the platform. You just always show both firms. And then we've got these 3 other policies here. So first of all, you can just kind of see at the top line how many of these outcomes have constant prices. In the base model with no intervention, you typically have, you know, constant prices. But then if you implement PDP, suddenly you never have almost never have constant prices. Okay. What happens, again, I don't want you to try to process this entire table. I just want to focus. So what I'm just going to focus on is this line here that says the high profit firms share. And what this does is this measures over time, like over, say, 100,000 periods, you know, the ratio of the 2 firms' profits, the algorithm's profits. Okay, now remember, within a given period, this ratio should be highly skewed because, you know, 1 firm is going to get most of the demand. I think this is for gamma 0.7, okay? But nonetheless, with no intervention, we see actually this ratio, well, it's equal to about 50%, okay? If we implement PDP, it's actually almost even closer to 50%, which means the firms are rotating demand. They're finding a way either with a price cycle, okay, or allowing the platform to randomize for them by charging the same price. They're finding a way to rotate demand between themselves, okay? Now, what happens with dynamic PDP, and especially with smarter AI, is that you now, even over a long horizon, you get highly asymmetric outcomes. So now, so again, look at smarter AI. you get around 80, you get the high profit firm, again, over 100,000 periods, say, getting a very 84% of the industry profits. Okay, so this means that the dynamic PDP policy, especially smarter AI, is making it a lot more difficult for firms to rotate demand and kind of split the market between themselves. And remember, demand rotation is classically considered to be a marker of collusion. And so it's reassuring and intuitive that the way these algorithms, or I should say the way these steering policies seem to benefit consumers is by breaking the ability of firms to rotate demand and split profits over time. Okay. So again, these policies implement the pricing patterns. This algorithms still sometimes do pretty good at splitting profits equally, except when you implement these more sophisticated policies. Okay. Now I only have a few minutes left, so I'm just going to say a few words, which is I've been talking about per unit fees, but you could also look at revenue sharing. The results are different. It's less likely that the platform benefits from these policies. It still benefits if it cares, enough about consumer surplus, for example, as a proxy for a competitive environment. But revenue sharing is more complicated. We have a number of other extensions. I guess I won't really say much more about them now, except maybe just to choose maybe one or two of these. I guess I'll focus on the last one here. We've been focusing on the case with 3 firms or 2 firms, but we can also look at the case of 2 firms. And one question you can ask in that situation is, well, if you have 3 total merchants, do you want to show one of them or 2 of them, right? Assuming you want to implement some sort of demand steering policy. And, what we find is that it actually, well, first of all, we find that there's a similar trade-off. And if you show more firms, 2 firms rather than 1 firm, that the way the algorithms respond in their converged strategies is actually by raising their prices. But on the other hand, when you show 2 firms instead of 1, you're also increasing the variety that's available to consumers. So you see that same trade-off that we discussed earlier. And you see it also with the algorithms, with what they actually do. The effects on consumer surplus are less clear, in particular with PDP or with smarter AI. Showing 2 rather than 1 firm is beneficial, whereas with just regular dynamic PDP, that's actually not beneficial. In all cases, well, certainly for the dynamic PDP, you never want to show all 3 firms. If you show all 3 firms, okay, you get more variety, but then you get much higher prices. So the question is, how much would you like to limit consumer choice? Okay, and then just to conclude, what we've done is we've looked at some very simple demand steering policies, and we looked at them from a theoretical standpoint, and also using very, very simple AI trained algorithms. Okay, and what we show is that in competitive markets, at least from a theoretical standpoint, and sometimes with the algorithms, consumers can benefit even though you limit their choice, and the platform can also benefit. In other situations, however, you need more subtle policies, and just the very, very simple policy of only showing the low-priced firm can actually backfire and harm consumers. But the good news is that we have found some more subtle policies that, at least in our simulations, seem to exhibit very good properties and often benefit not only consumers, but also the platform. And that's it. Thank you so much. And if you have any questions, of course, I'm